Hey y'all, welcome to Miss Clark's chemistry class. This is the fourth lesson in a series of lessons about redox reactions. Did you know that we could use redox reactions to generate electricity? That's where the whole genre called electrochemistry comes from. That's what this lesson is going to talk about. How can we create electricity using redox reactions? Go get your notes, get something to write with. You're probably going to need a periodic table, and let's get started. We are still talking about redox reactions, but in this lesson, we're going to talk about why redox reactions. What's the purpose of them? Up until now, we've learned about how to identify them, what part is being oxidized, what part is being reduced. Now we're going to talk about what good is redox reactions in the world. Electrochemistry is ran by redox reactions. Let's talk about that. Let's look at that word, electrochemistry. Electro, that makes us think of electricity. I realize that's a very, very, very simplified definition of electricity, but that's what it is, the movement of charges. And since redox reactions move electrons, which are charges, we can cause this to happen. We can create energy with a redox reaction. This is how batteries are made. Now, we can create two different types of cells using a redox reaction. Now, the whole idea of being able to use a redox reaction, you're going to have to separate the half reactions out. You're going to have the half reaction that deals with oxidation in one container, and you're going to have the reaction that does the reduction in a separate container. And you're going to drive this charge. Driving this charge means moving electricity, which means we're creating electricity with chemical reactions. Okay, so the first type of cell we're going to talk about is called a galvanic cell. Another word for galvanic cell is a voltaic cell. This is the type of cell, or this is the type of battery that will create a spontaneous redox reaction. This is important. This is what we want, a spontaneous reaction. Again, we're going to have to split our redox reaction into these half reactions to generate the electricity. So we're going to separate the redox reactions into the oxidation part and the reduction part. This is going to be the majority of this lesson, galvanic cells. We're going to talk about, in this level of chemistry, how to get these spontaneous reactions. A good example of what a galvanic cell is, are these the batteries that you would use in just about any of your devices. Now, not rechargeable batteries, regular batteries, like a 9-volt battery. You know the 9-volt battery, it's kind of like this, and it's got that little part here, and then if you stick it to your tongue, it kind of makes a little shock. This is the type of battery that I'm talking about. But let's go ahead and get a definition for the other kind of cell that redox reactions can create, and that's called an electrolytic cell. Let's look at that word electro again. That means we're going to have to put in electricity. It is non-spontaneous. A galvanic cell, spontaneous reaction, we hook it up and it just goes on its own. Spontaneous. A non-spontaneous cell is when you have to add electricity in. We're going to have to add electricity to make this one go. This is more of an AP chemistry topic. We're going to stick to more of the pre-AP chemistry topic, which is going to be the galvanic cells. Okay, so let's take a look to see what a simplified galvanic cell looks like. I'm going to draw the cell, and then I'm going to apply redox to the cell. The first thing that we're going to need is 2 beakers. These are going to have aqueous solution in them. So let's go ahead and put solution. Now, in one of these beakers, you're going to have a metal, and in the other beaker, you're going to have a different metal. We need to have some kind of voltage meter. We're going to connect these 2 pieces of metal. And remember, we talked about electricity just being the flow of charges. Well, if we think about a redox reaction, we're going to have half of the reaction losing electrons, and we're going to have the other half of the reaction gaining electrons. So if we hook this cell up, this is what the basic cell is going to look like. Electrons are going to be pulled from one piece of metal, and they're going to be donated to the other piece of metal. We're moving electrons. We're moving a charge. We're creating electricity. This should be a number that tells us how many volts of electricity we're creating. Now, if we want our electrons to leave, then we have to put the oxidation at the side we want the electrons to leave. Because remember, oxidation means we're losing electrons. When you put the oxidation at one side, that side is then called the anode. The anode is always the side that has electrons leaving, and electrons leaving is oxidation. So oxidation always happens at the anode. Electrons are coming in on this side. Well, we gain electrons. That's called reduction. So the reduction is going to be on the other side because we're gaining electrons. The side that's gaining electrons, this is called the cathode. Anode, cathode. Oxidation happens at the anode. Reduction happens at the cathode. So if you need a memory device to help you this, I've got anox and red cat. At the anode, you've got oxidation, and at the cathode, you have reduction. Red cat, anox. The electrons are going from the anode to the cathode. From the anode to the cathode. So electron flow from the anode to the cathode, fat cat. Okay, we need a couple of more vocab words right here. This piece of metal and this piece of metal, these are called electrodes. This is going to be an aqueous solution. Now let's think about something. If electrons are constantly leaving here, electrons are leaving. That means we're going to run out of electrons eventually over here. And if electrons are gaining over here, gain, we're building up too many electrons here. So we need to add something to this that's going to help everything stay more in balance. We're going to call this a salt bridge. Remember, salt, that's just a generic term for ionic compounds. We could use salt, we could use NaCl, or you could use potassium nitrate. There's lots of other salts that you could use. The function of the salt, though, in the salt bridge, is to replenish charges. We just said that from over here, the oxidation side, we're losing electrons. So we could really use a supply of electrons. So the salt bridge is going to be pushing negative anions this direction. And it's going to be pushing positive cations this direction. And let's notice something. Anions are being attracted to the anode. Cations are being attracted to the cathode. And again, the salt bridge, that's just to keep those charges replenished because we're constantly losing electrons here and we're constantly gaining electrons here. In this instance, our electrode is zinc. And so what is happening here, if we want to zoom in, we're having our zinc losing an electron. Actually, our zinc is going to lose 2 electrons and become zinc plus 2. So when we get a little zinc to break off, it's going to break down into its cation and those 2 electrons. Well, those 2 electrons, they're going, and they're going to go through the voltmeter and they're going to go to the other side, creating electricity. So what's left over swimming around in our aqueous solution is just going to be this zinc ion. And then if we go look on the other side, the electrons coming in, when it hits this solution, there's a lot of copper ions hanging out. And so we're going to have our copper ion, and it's going to grab up 2 electrons, and then it's going to form copper, which is what this electrode is, copper. So you might be able to see that this is going to run out eventually. One day, we will run out of zinc metal to produce electrons. And we are building up copper over here. So at our anode, this metal is eventually going to deteriorate and disappear. And over here, we're building up. We're going to have an excess of copper building up onto the copper metal. Because every time one of these electrons comes in, bonds up one of these coppers to make a copper element, it's then going to stick on to here. It's going to stick onto the electrode. So for every time, we're going to have a little bit more stick on, a little bit more stick on, a little bit more stick on, a little bit more stick on. So you see how we're kind of putting more copper onto this electrode while we're eating away at this zinc. Okay, so let's make sure we got a couple of things from my little scribble scrabble from before. Let's make sure and know that these metal pieces, these are electrodes. They're where the free element is, zinc, copper. The ions are in the solution. The electrons are flowing from the anode to the cathode. The electrons are flowing from the anode to the cathode. That's that fat cat. From the anode to the cathode. Let's also remember that the anode is going to be negatively charged. Remember, like charges don't like each other. That's what's pushing these electrons away. Electrons are negative, They're at the negative side, so they're being pushed away to the positive side. Anodes are negative. I like to remember that because it's got an N right there in the middle of it. At the anode is where oxidation is happening, anox. At the anode is where oxidation is happening. The electrons are leaving. We're losing electrons. We're traveling over to the reduction side, the cathode. The cathode is always positive. That's what's attracting these electrons in, is that positive cathode. Reduction happens at the cathode, red cat. Remember, the electrons are flowing from the anode to the cathode. This is also called an electrode, and the electrons are coming in. We've got our salt bridge, and our salt bridge is feeding negative anions towards the anode and positive cations towards the cathode. And that's just to replenish. When you have your oxidation at the anode and your reduction at the cathode, these electrons will just automatically start flowing. That's what it's called, spontaneous. If this was flipped and we were going to call this side the anode, nothing would happen because the electron flow would not go in the right order to create electricity. Okay? So I'm hoping you're getting all of the parts of a galvanic cell or a voltaic cell. Anode, cathode, which direction the anions are going, the cations, why they're going a direction, which directions the electrons are going from the anode to the cathode. You need to be able to draw this. Okay, so one more time, the electron flow goes from the anode to the cathode. And since our electrons are flowing that way, the anode is negative. That's what makes the electrons want to leave. That's also what's causing our anode electrode to be eaten away, that loss of electron. Remember, the cathode is positive. That's why the electrons are being attracted to it. And it's also the reason why the cathode is being coated with more elements. The cathode is getting bigger. The anode is getting smaller. Now, we can show everything that's happening in a galvanic cell in a shorthand called line notation. If we had a redox reaction, if we were to figure this out, copper is losing 2 electrons. That means it's being oxidized. Silver is gaining an electron, so it's being reduced. Okay, so remember, our anode metal, that is our oxidized metal. Oxidized metal, that's copper. Then we're going to put a line. Then you need your anode ion. Your anode ion, that's copper 2+, right? Because your oxidation is going to go together. Then you're going to do double lines, and then you need your cathode ion. Well, your cathode ion, that's your reduction. Reduction is silver, and our ion is the Ag+, and then one line and the cathode metal. So it's always going to be metal, ion, ion, metal. It's always going to be the anode and then the cathode. And that's just a little shorthand to show what's happening in the cell, what's the oxidation, what's the reduction, because anode's always oxidation, cathode's always reduction. Now that we've talked about the galvanic cell, let's go back to the electrolytic cell for a second. Remember, the main difference between an electrolytic cell and a galvanic cell was that the galvanic cell was spontaneous because you had that positive voltage. An electrolytic cell will only work if you add electricity into the cell itself. That's why here it's talking about a voltage source in my little image. But I wanted to talk about a really common use for an electrolytic cell, and that is electroplating. And that's where you plate one type of metal on another type of metal. In fact, a lot of the old silverware that might be packed up in your grandma's trunk that she only takes out on special occasions, a lot of that silverware is made this way. And that's what I've got an image of here. So we had this spoon, which was composed of not pure silver, but some other metal alloy. And then you put this silver plate as an anode, and you have this silver nitrate solution. When these electrons come over through the wire, then they're going to grab a hold of these silver ions, and they're going to become silver atoms, and they're going to plate on this spoon. Anyway, electrolytic cell, I didn't really say very much about it, so I kind of wanted to circle back to it and talk about electroplating. Also, some differences between galvanic cell and electrolytic cell. A galvanic cell, that's going to be like your single-use batteries, and an electrolytic cell would be like your rechargeable batteries. You have to add energy into it, use it, add more energy into it, Anyway, I just wanted to wrap up with touching back on the electrolytic cell. And you thought chemistry did not apply to your real life. All of those batteries that you're using for all of your devices, redox reactions. Bam, chemistry in your real world. Now, I still have a few more videos left in this series. We still have to learn how to calculate how much voltage of electricity we're creating with this redox reaction. That's in the next lesson, so make sure and stay tuned. Until next time, bye y'all.